Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Saturn has always held a peculiar place in the collective imagination, a planet at once majestic and enigmatic, whose pale banded face and dazzling rings set it apart from all other worlds in the solar system. To behold Saturn is to meet elegance writ large across the heavens, an immense globe of shifting storms, subtle colors, and a ring system so complex and delicate that it challenges our ideas about what a planet can be. Yet for all its beauty, Saturn is also a laboratory of extremes, a place where physics, chemistry, and time combine to sculpt phenomena that test the limits of human understanding. This exploration of Saturn and its magnificent rings will take you from the first telescopic glimpses that hinted at something extraordinary through modern spacecraft discoveries that revealed an intricate, dynamic system, and beyond into what the future might hold for study and discovery. Throughout, the story of Saturn is one of wonder, of science pushing to make sense of complexity, and of the deep interplay between observation and imagination. From Earth, Saturn is a bright, steady point of light that wanders against the starry backdrop. Historically, it was one of the wandering lights known to ancient peoples, a slowly moving marker in the sky associated with time, harvests, and deities. When telescopes first became tools of curiosity and knowledge, observers were startled by the odd silhouette that trailed Saturn. For a time, the outline suggested ears or handles. Only careful telescopic work gradually revealed that the planet was girdled by a flat, extensive structure. The name given to this feature evokes glory and wonder: the rings. Early astronomers struggled to explain the rings' appearance. The puzzle was as much philosophical as scientific because rings blurred the categories people use for celestial bodies. Planets had been spheres. Comets streaked across the sky. Stars were fixed. Here was a new kind of geometry in the heavens, a flattened composite structure that demanded new thinking about matter, motion, and the forces that could sustain such a system. Saturn itself is a gas giant, second in size only to Jupiter within the family of planets around our star. Its bulk is mostly hydrogen and helium, lighter elements that dominate the composition of the Sun and the bright envelopes of the largest planets. Yet Saturn's internal story is shaped as much by what lies beneath those hydrogen curtains as by the clouds we see. Deeper inside, gravity has pressed hydrogen into states that would be alien at Earth's surface. Under immense pressure, hydrogen behaves as a metallic fluid that conducts electricity, helping to power Saturn's magnetic field. The planet's size and low density combine to tell a counterintuitive tale. Though Saturn is about 9 times wider than Earth, it is so light for its volume that it would float in a sufficiently large body of water. This fact is less a practical suggestion and more a poetic reminder that mighty and density are separate aspects of planetary identity. Saturn's atmosphere is a theater of motion. Beneath the pale yellow and gold veils lie bands of cloud and wind, whose contrasts are more subtle than Jupiter's, but no less dramatic. Jet streams race around the planet, producing banding that can be seen by careful telescopic observation. Storms sometimes erupt, enormous weather systems that circle the planet for months, driven by internal heat and the dynamics of fast winds. Observers have watched a particular storm system, known as the Great White Spot, appear intermittently in Saturn's atmosphere, a storm event that resembles, in miniature and cadence, Jupiter's Great Red Spot, but with its own behavior and life cycle. The winds at Saturn's cloud tops can reach high speeds, sculpting vortices and waves that propagate vast distances. Coloration in the atmosphere is the result of complex chemistry and sunlight interacting with trace compounds, producing shades that shift with altitude and latitude, and that reveals subtle cues about temperature, composition, and dynamics. If Saturn's atmosphere and internal structure shape the planet's character, its rings define the public image. The rings are a massive, thin disk of countless particles ranging in size from micrometers to meters, composed largely of water ice and a small fraction of rocky material. Seen edge-on from Earth, the rings can occasionally appear to vanish, because their thickness is only a few tens of meters despite spreading outward for hundreds of thousands of kilometers. From nearly any vantage point that allows a broad view, however, the rings announce themselves with unrivaled beauty. They are not a single consistent structure, but a series of rings, gaps, and divisions, each with subtle variations in particle size, density, and dynamics. The broadest and most prominent bands are named in an alphabetical convention that traces back to early studies. Each exhibits its own set of features, including narrow ringlets, clumps, and waves excited by gravitational interactions with Saturn's moons. The origin of the rings is a subject that has invited much debate and several hypotheses. One prevailing view suggests that the rings are relatively young in geological terms, perhaps only a few 100 million years old, formed from the debris of a shattered moon or from material left over from the planet's formation that never coalesced into a larger body. Collisions and tidal forces play decisive roles in shaping ring systems. Within a certain distance of Saturn, known as the Rauch limit, the planet's tidal gravity prevents material from aggregating into a single solid body. Instead, fragments are stretched, ground down, and maintained in orbit as a disk. The fine balance between Saturn's pull and the mutual gravity of ring particles creates a dynamic equilibrium where structures can assemble and disassemble. Evidence from spacecraft, particularly the Cassini mission, supports the notion of active processes. Meteoroid bombardment slowly darkens and erodes ring material, while gravitational perturbations from moons and embedded moonlets carve gaps, shepherd ring edges, and create spiral density waves. Cassini changed our understanding of Saturn in profound ways. When that ambitious spacecraft reached Saturn, it became the first instrument to orbit the planet for an extended period, providing an intimate, long-term view of both the planet and its rings. Cassini's observations revealed surprising complexity. The rings are active and ephemeral in their characteristics, with phenomena such as propeller-shaped disturbances caused by small embedded objects, wakes produced by shepherd moons, and seasonal changes that affect the ring's appearance and behavior. Observations of spokes, transient radial features that appear in the rings and rotate with the planet, challenged prior assumptions and hinted at the role of electromagnetic interactions in ring dynamics. These spokes, dark or bright depending on viewing geometry, seem linked to the planet's magnetic environment and the charging of icy particles. Cassini's final descent into Saturn's atmosphere, in a deliberate, sacrificial maneuver, provided unique in situ measurements of the innermost ring environment and samples of the Caesan dust close to the planet, enriching our knowledge in ways that remote observation cannot replicate. Saturn's moons are partners in the drama. With more than 80 known satellites, Saturn hosts an array of worlds as varied as a miniature planetary system. Tiny moonlets embedded within the rings sculpt local structure, while large moons such as Titan and Enceladus have become focal points in the search for conditions that might support life or prebiotic chemistry. Titan is intriguing because it is shrouded in a thick, nitrogen-rich atmosphere with a methane cycle that mirrors Earth's hydrological cycle in form, if not in substance. Lakes and seas of liquid methane and ethane dot Titan's surface, while complex organic chemistry in its upper atmosphere produces an orange haze of hydrocarbons. Voyager first revealed the basics of Titan's atmosphere, and Cassini, together with the Huygens probe that descended to Titan's surface, opened an entirely new chapter. Huygens sent back images of channels and rounded rocks, pointing to processes akin to river erosion by liquid hydrocarbons, while Cassini's radar pierced the atmospheric veil to map Titan's varied landscapes and seasonal changes. Enceladus, smaller but perhaps more scientifically provocative, surprised researchers with active geysers erupting from fractures near its south pole. Jets of water vapor and icy particles stream into space, creating a faint atmosphere around Enceladus and contributing material to Saturn's E-ring, a diffuse ring that lies beyond the main rings. Cassini flew through these plumes and directly sampled their composition, detecting water vapor, organic molecules, salts, and tiny silica particles that suggest hydrothermal activity on Enceladus's ocean-bearing seafloor. The implications are profound: an internal ocean in contact with a rocky core, warm enough to drive chemical reactions, could provide the chemical energy and environment favorable to microbial life as we understand it. Enceladus thus shifted the center of astrobiological interest in the Saturnian system, becoming a key target for any future missions aimed at assessing habitability beyond Earth. The interplay between the rings and the moons is a choreography shaped by gravity. Moons can shepherd ring edges, holding narrow rings in place through resonant interactions, while other moons create gaps, such as the famous Cassini division, a wide gap between Saturn's A and B rings that is carved primarily by gravitational resonances with the moon Mimas. Smaller embedded moons create density waves and propeller features in the rings, revealing that even minute bodies can have outsized impacts in a low-gravity, collisional environment. The rings, in turn, act back on the moons by providing torque that can alter their orbits over long timescales. This gravitational give and take paints a picture of a system in constant, measured evolution, a slow dance that has been unfolding for eons and that continues to shift the architecture of the Saturnian neighborhood. Compositionally, the rings are dominated by water ice, a fact that is both beautiful and informative. The high albedo of the rings, their capacity to reflect sunlight, arises from the pristine nature of ice surfaces. Yet no region of the solar system is completely immune to contamination. Micrometeoroid bombardment and the gradual darkening by organic-rich materials slowly alter ring brightness and color. Spectroscopic analysis has revealed variations in ice purity across different ring regions, with certain bands showing more contamination, which hints at differing ages, histories of deposition. The presence of trace organic compounds in ring particles and in the spray from Enceladus adds chemical richness to the system, connecting processes across moons and rings in a web of material exchange. Ring dynamics are a field of study that combines celestial mechanics, fluid dynamics, and granular physics. Because ring particles collide frequently, their behavior often resembles that of a granular flow more than a collisionless swarm of asteroids. Collisions dissipate energy, keeping relative velocities low and enabling the formation of coherent structures like ringlets. The density of particles in a region affects how self-gravity can aggregate clumps temporarily, leading to wakes and short-lived clumps that's sheared by differential rotation. Waves, both spiral density waves and bending waves, propagate through the rings as the gravitational signatures of moons sweep across the disk. Analogs to wave phenomena in fluids emerge, demonstrating that even in a regime dominated by gravitation and collisions, patterns familiar from other branches of physics can arise. Saturn's magnetic field is another defining feature. Generated deep within the planet by the motion of conducting fluids, the magnetic field interacts with the solar wind and with charged dust and plasma in the ring system. Magnetic influences can charge icy grains, giving rise to electric forces that act in concert with gravity. These forces may help explain transient spokes and other ephemeral ring phenomena. The magnetic environment also shapes the radiation belts that encircle the planet and affects the surfaces of moons, especially those that ride close to the magnetosphere's energetic particle populations. Observations of radio emissions and auroral activity on Saturn provide windows into magnetospheric dynamics, coupling the planet's interior with its space environment. Seasons on Saturn, governed by the planet's tilt and its orbit around the Sun, unfold over nearly 3 decades each because Saturn takes about 30 Earth years to complete a solar circuit. Seasonal changes affect atmospheric, chemistry, and circulation patterns, alter the illumination of the rings, and even influence the visibility of certain features. For example, the amount and appearance of spokes in the rings can vary with the angle of sunlight, highlighting how geometric perspective and seasonal axes sculpt what observers see. The slow, languid progression of Saturn's seasons reveals the value of long-duration missions. To understand the planet fully requires patient observation across years and decades, a lesson that Cassini embodied by staying in orbit for 13 years and witnessing seasonal transitions that shorter missions could not. Looking outward to the broader context of planetary formation, Saturn's rings and moons offer clues about processes that were common in the young solar system. Studying the structure and composition of ring particles helps constrain the environment in which the planet evolved and the mechanisms that distribute mass within circumplanetary disks. The formation of moons from ring material, or the disintegration of moons back into rings, speaks to the fluidity of planetary architecture in which bodies coalesce and disperse depending on dynamics and chance collisions. Comparative studies with rings around other gas giants such as Jupiter, Uranus, and Neptune, where rings are faint and sparse in comparison, deepen our understanding of why Saturn in particular boasts such an abundant ring system. Is it a product of chance, of unique collisional history, or of subtle differences in the environment around Saturn during its formation? These questions continue to animate research and catalyze new missions in theoretical work. Technological achievement and scientific curiosity combine to let humanity touch the Saturnian system in an unprecedented way. The Voyager spacecraft provided the first close-up views of Saturn in the early 1980s, cataloging rings and moons in extraordinary detail and opening new questions about the system's complexity. Decades later, Cassini's arrival and long mission provided comprehensive data sets across wavelengths and instruments, transforming Saturn from a remote point of light into a complex laboratory of planetary processes. Huygens' descent through Titan's dense atmosphere to land upon its surface stands as a milestone in planetary exploration, demonstrating humanity's capacity to reach and probe exotic environments. These missions relied on ingenuity in spacecraft design, navigation, and instrumentation, and they yielded tangible instruments of discovery: radar maps, spectroscopic profiles, dust analyzers, plasma detectors, and cameras that captured the interplay of light and shadow across rings and moons. But the Saturn story does not end with Cassini. Future missions and proposed concepts aim to build on the richness of past discoveries. Proposals range from orbiters that could provide high-resolution mapping and long-term monitoring to probes that would plunge into Saturn's atmosphere to sample its composition directly, measuring noble gas abundances and isotopic ratios that encode the planet's formation history. There are tantalizing ideas for sample return missions to Enceladus or other moons, seeking to bring pristine material back to Earth for analysis of organic chemistry and potential biosignatures. The engineering challenges are formidable: the enigmatic high radiation environment, the need for precision navigation in a system filled with small debris, and the requirement for instruments capable of detecting subtle chemical markers. Yet the scientific payoff could be immense, clarifying not only the story of Saturn, but also the broader question of how common habitable environments like subsurface oceans might be across the galaxy. The cultural resonance of Saturn extends beyond scientific publications and mission briefings. Artists, poets, and storytellers have long been seduced by the planet's ring silhouette. When the first photographs of Saturn's rings reached the public, they stirred a sense of the uncanny, a natural object that arranged itself in an almost architectural form. In many ways, Saturn has become a symbol of the sublime in nature. Beauty that implies power, elegance that hints at dangerous forces, and complexity that resists simple comprehension. The ring planet has inspired imagery in literature and film, shaping our cosmic myth-making and inviting metaphors for human endeavors. Yet this cultural layer sits atop a foundation of rigorous observation, where each poetic impulse finds its counterpart in data, models, and careful inference. Educationally, Saturn provides a rich platform to introduce core concepts in physics and astronomy. The rings teach about orbital motion, collision dynamics, and resonance. The moons demonstrate tidal heating, atmospheric chemistry, and the variety of planetary bodies that can exist in a single system. Saturn's magnetosphere and auroras illustrate electromagnetic effects on planetary scales, while the planet's formation history connects to the broader narrative of how planetary systems emerge from disks of gas and dust. For students and curious minds, Saturn encapsulates a remarkably wide set of phenomena within a single cohesive system, making it an invaluable natural laboratory for teaching scientific thinking and observational techniques. Saturn also forces us to confront scale in ways that few objects do. The rings, spanning hundreds of thousands of kilometers, are nevertheless thin, a tiny fraction of their radial extent and vertical thickness. The moons range in size from house-sized boulders to Titan, larger than the planet Mercury. Storms hundreds of kilometers across swirl in an atmosphere whose depths are hidden beneath reflective clouds. Timescales span the immediate, the transient spokes, short-lived clumps, and passing shadows, to the immense, the slow migration of moon orbits, the potential gradual decay of ring material under meteoroid bombardment, and the evolutionary timescales of planetary atmospheres. This juxtaposition of scale invites humility. Our models and instruments capture snapshots and trends, but the full life of the Saturnian system unfolds on timelines that challenge human patience and planning. Environmental considerations also enter the discourse around Saturn exploration. Missions that venture into exotic worlds bring with them responsibilities to avoid contaminating potentially habitable environments. The discovery of subsurface oceans and organic chemistry on moons like Enceladus and Titan raises ethical questions about forward contamination and planetary protection. Space agencies have developed guidelines to minimize the risk of introducing terrestrial microbes to environments that might be capable of supporting life. Future missions must balance the drive for discovery with careful stewardship, ensuring that the quest to understand does not inadvertently compromise the very systems we seek to study. Public engagement with Saturn has been elevated by the stunning images and discoveries sent back by spacecraft and by the continuing parade of new findings interpreted for broader audiences. The image of a ring plane crossing, the sight of shadowed petals of the rings against the planet, and the raw data suggesting internal oceans on small moons capture imaginations and drive public support for exploration. Outreach programs link scientific teams with classrooms, amateur astronomers, and online communities, fostering a sense of global participation in discovery. The narratives built around Saturn, of hidden oceans, of active geysers, of the cosmic dance between rings and moons, create compelling stories that bridge the gap between technical research and everyday wonder. From a philosophical vantage, Saturn and its rings provoke reflection on what it means to categorize and understand the natural world. The rings resist easy classification. They are neither solid nor entirely diffuse, neither permanent nor wholly transient. They embody process, change, and the idea that natural systems may be in states of continuous flux instead of static balance. The planet's moons complicate the simple hierarchy of planets and satellites by exhibiting features that blur the line between worlds capable of hosting life and mere inert rocks. This complexity nudges science toward an appreciation of nuance, encouraging refined models that account for interlinked processes and emergent behavior. Saturn thus stands as a reminder that the universe often prefers complexity over simplicity, and that deep understanding requires both careful measurement and conceptual flexibility. As we look ahead, Saturn remains an irresistible destination for scientific inquiry. Questions persist about the ring's age and ultimate fate, the prevalence and nature of subsurface oceans, the detailed chemistry of Titan's organic-rich environment, and the deep interior dynamics that generate magnetic fields and global heat flows. Technological advances in propulsion, miniaturized instrumentation, and long-lived power systems will open new possibilities for sustained presence in the Saturnian system, perhaps enabling distributed networks of probes, subsurface penetrators, or even sample return missions that bring the raw chemistry of distant worlds to Earth laboratories. Each new generation of instruments will sharpen our view and deepen our questions, continuing in the cycle of discovery that defines planetary science. The human story of Saturn is, at its heart, about curiosity made concrete. From the first telescopic observations that revealed a strange appendage to a bright point of light, to the intimate reconnaissance by robotic emissaries that circled and sampled the system, humankind has progressively peeled back layers of mystery. With every advance, the planet reveals fresh subtleties: waves in a ringlet, salt grains in an icy plume, a methane river valley carved on a cold moon. These discoveries do not exhaust the wonder, but rather refocus it, offering ever more refined mysteries to unravel. In this way, Saturn's magnificence is not merely aesthetic, but epistemic. It is a vast reservoir of learning that shapes how we think about planets, the conditions for life, and the processes that assemble and transform worlds. To stand, even in imagination, near Saturn is to encounter a world that is both familiar and alien. Its bands and storms echo the weathered face of Jupiter, yet its rings introduce a wholly different architecture. Its moons are scaled-down versions of planetary diversity, hosting atmospheres, oceans, geysers, and barren rock. The rings themselves are a statement about the fragility and tenacity of ordered structure amid chaos. Particles that collide endlessly yet maintain coherent, sculptured patterns thanks to gravity and resonance. For scientists and dreamers alike, Saturn invites a particular kind of attention: patient, careful, and open to surprise. It rewards those who observe across seasons and who bring multiple instruments and perspectives to bear. In the end, Saturn is more than the sum of its parts. It is an emblem of the solar system's capacity to produce forms of grandeur that are at once delicate and overwhelming. Its rings shimmer as a delicate ornament, yet speak to violent processes of fragmentation and erosion. Its moons whisper secrets of potential, habitability, and chemical complexity. Its atmosphere, spinning and boiling in enormous vortices, reminds us that even gas giants have personalities, moods, and histories. To study Saturn is to engage with a nexus of disciplines: physics, chemistry, geology, fluid dynamics, and even philosophy of science. It is to practice an integrative science that knits together data from photons, particles, and gravitational tugs into two coherent narratives. As scientific instruments become more sensitive and missions more ambitious, Saturn will continue to yield surprises. The planet and its rings are a dynamic tableau, a stage where microphysics and celestial mechanics perform in concert. Whether through advanced telescopes, subsurface probes to icy moons, or perhaps someday even human-guided robotic explorers operating with unprecedented autonomy, the future promises an even richer appreciation of what Saturn has to teach. For now, we can revel in the achievements of past exploration and in the horizon of possibilities that lie ahead. The ring planet remains a jewel of the solar system, a testament to nature's capacity for creating structures of both sublime beauty and enduring scientific significance. Saturn's influence stretches beyond its immediate system, extending into the broader philosophical questions about how planetary systems evolve and how the diverse architectures of exoplanetary systems in our galaxy compare with our own. As astronomers catalog thousands of exoplanets orbiting distant stars, they search for analogs to Saturn, worlds with extensive ring systems, moons, or complex atmospheric dynamics. While direct detection of rings around exoplanets is challenging due to the vast distances involved, some transit observations hint at the possibility of giant ring systems dwarfing even Saturn's, suggesting that nature may be even more inventive than previously thought. Saturn thus becomes a touchstone for interpreting data from afar. Its physical processes, atmospheric chemistry, and dynamic interactions between rings and moons establish reference models for understanding similar signatures detected around other stars. These comparisons also illuminate how special and rare a structure like Saturn's rings may be. If the rings are indeed relatively young, their presence during humanity's technological age could be a coincidence on cosmic scales. This raises questions about whether we are witnessing Saturn at a particular moment in its evolution, one where the rings are still bright and icy before they darken and dissipate. Cassini's data suggested that ring material is slowly spiraling inward toward the planet, a ring rain that deposits water molecules and tiny charged particles into Saturn's atmosphere. Over millions of years, this process may erode the rings significantly. Astronomers contemplating the distant future imagine a time when Saturn's rings, once a glorious halo of light, might fade into near invisibility. The ephemeral nature of the rings adds poignancy to our observations and underscores the value of studying processes that operate over long timescales. Even as the rings evolve, Saturn remains a planet of ceaseless activity. The hexagon at its north pole is one of the most fascinating atmospheric features in the solar system. First observed by the Voyager missions and later studied extensively by Cassini, this six-sided jet stream pattern defies easy explanation. Unlike storms or vortices, the hexagon is a standing wave structure in Saturn's atmosphere. It rotates with nearly the same period as the planet's interior, but retains rigid geometric boundaries. Laboratory experiments and fluid dynamic models suggest that flows with differential rotation can produce polygonal patterns. Yet Saturn's hexagon remains a striking natural instance of this phenomenon on a colossal scale, spanning roughly 30,000 kilometers across. Within this hexagon lies a massive, swirling vortex with a central eye reminiscent of hurricanes on Earth, but far more immense. A churning reminder that gas giant weather systems operate with tremendous energy and complexity. Saturn's southern hemisphere has its own distinctive atmospheric phenomena, though it lacks a perfectly geometric analog. There, intense storms and massive jet streams produce striking cloud structures that vary with season. When Cassini observed a powerful southern storm during one of its phases, scientists witnessed lightning and convective towers piercing the atmospheric layers, revealing that Saturn's storms can reach deep into its gaseous envelope. These storms are fueled by the release of internal heat, which radiates outward from the planet's interior. In fact, Saturn emits more energy than it receives from the Sun. This excess heat drives atmospheric circulation patterns and may be tied to helium differentiation deep inside the planet, where helium droplets rain downward through metallic hydrogen layers, releasing gravitational energy as heat. Such internal processes serve as reminders that giant planets are not passive bodies but dynamic, heat-powered machines over their entire lifespan. Among Saturn's moons, diversity reigns. Mimas, often compared to the Death Star from popular culture, because of its large Herschel crater, plays an outsized gravitational role. Despite its relatively small size, Mimas induces resonances that shape the rings and help maintain features like the Cassini division. Meanwhile, the larger moon Tethys displays massive fractures and enormous impact basins that hint at a tumultuous past. Dione and Rhea, mid-sized moons rich in water ice, exhibit evidence of resurfacing and tectonic history, with bright ice cliffs and wispy terrains created by past geological activity. Phoebe, a captured object from the distant Kuiper Belt, offers insight into the primordial outer solar system. Retrograde in its orbit and possessing a composition similar to trans-Neptunian objects, Phoebe is a relic of formation processes far from Saturn. Its presence broadens our understanding of how objects migrate inward, become trapped by giant planets, and enrich satellite systems with exotic material. Dust from such distant, irregular moons may contribute darker material to Saturn's outer ring regions, hinting at exchanges of particles across vast distances within the system. The shepherd moons, among them Prometheus, Pandora, and Atlas, demonstrate in miniature how gravitational interactions sculpt ring edges. Prometheus, for instance, periodically dips into the F-ring, drawing out streamers of material and producing rippled channels that shift over time. This ongoing tug-of-war between small moons and ring particles creates structures that seem impossibly delicate, yet persist through years of observation. Such moons are small enough that they cannot pull themselves into perfect spheres, yet their influence is immense when measured in ring morphology. One of the most captivating revelations from Cassini was the existence of seasonal changes, not just on Saturn itself, but across its largest moons and rings. Titan undergoes a methane monsoon cycle that shifts as the hemisphere tilted toward the sun changes. Over the course of Cassini's mission, scientists saw clouds gather near the equator, then migrate poleward as seasons advanced. Lakes in Titan's polar regions filled and receded, offering direct evidence of a repeating liquid cycle in a world far colder than Earth. These seasonal transformations gave Titan the distinction of being the only known place besides Earth with stable surface liquids and active weather cycles involving those liquids. The ring system also changes with the seasons due to illumination geometry. When the sun strikes the ring's edge on during equinox, shadows stretch dramatically across Saturn's upper atmosphere. This low-angle sunlight also reveals vertical warps and waves in the rings, subtle oscillations that normally go unnoticed. It is during these equinox periods that spokes are most commonly observed. Their appearance is a testament to the interconnectedness of sunlight, particle charging, magnetic interactions, and the microphysics of icy grains. Saturn's gravitational influence reaches even farther. Beyond the visible rings lies a vast system of tenuous ring arcs, dusty ejections from small moons, and the diffuse E and G rings shaped by the geysers of Enceladus and impacts on other moons. The faint Phoebe ring, discovered only recently, extends millions of kilometers outward and is believed to be fed by micrometeoroid strikes on Phoebe's surface. Though nearly invisible in reflected light, this enormous halo of dust contributes to the darkened appearance of Iapetus's leading hemisphere. As Iapetus plows through this dust cloud in its orbit, the dusty grains accumulate preferentially on one side, creating the stark two-tone contrast that has puzzled astronomers for centuries. Iapetus itself is another world of fascination, a moon with a dramatically dark leading hemisphere and a bright trailing one, marked by a tall equatorial ridge that resembles a planetary seam. The origin of this ridge remains debated, with hypotheses ranging from ancient ring remnants accreted onto the moon's surface to tectonic upwellings or even rapid early rotation that caused material to accumulate along its equator. Whatever the cause, Iapetus stands out as one of the strangest bodies in Saturn's domain. Long-term evolution of the Saturn system is shaped by tidal interactions that slowly alter moon orbits. Moons can migrate outward over time as energy is transferred from Saturn's rotation to orbital motion. This outward drift can push moons into orbital resonances that radically reshape the system. Many of Saturn's moons are locked into such resonances, producing tidal heating, maintaining orbital eccentricities, and governing the gravitational rhythms that influence the rings. Enceladus's internal ocean likely owes its continued warmth to tidal stresses induced by its orbital resonance with Dione. This delicate interplay between gravity and internal heat demonstrates that moons are not passive spheres, but dynamically evolving worlds with unique thermal histories. At the center of all this complexity remains Saturn itself, a planet whose internal structure is still partly shrouded in mystery. Researchers use gravity measurements, oscillations inferred from ring seismology, and magnetic field data to probe the planet's interior. One striking result from ring seismology, the study of waves within the rings caused by Saturn's internal vibrations, reveals that the planet may possess a diffuse, fuzzy core composed of a mixture of rock, acid ice, and metallic hydrogen that blurs the boundary between core and envelope. This diluted core model challenges traditional ideas of sharp core boundaries in gas giants and supports theories that giant planet interiors may be more mixed and fluid than previously thought. Ring seismology also demonstrates that the rings serve as a natural seismograph, responding to subtle oscillation modes deep within Saturn. These waves propagate through the rings as faint patterns, encoding information about processes far below the cloud tops. The fact that scientists can use the rings, a vast, icy disk, to study Saturn's internal structure shows how interconnected the system is and how seemingly separate components are part of a unified planetary story. Saturn's magnetic field presents another scientific enigma. Unlike Earth or Jupiter, Saturn's magnetic poles are almost perfectly aligned with its rotational axis. This unusual symmetry complicates attempts to determine Saturn's precise rotation rate because magnetic variations that normally reveal rotational speed are muted. Theories about the magnetic field's origin point to the unique conditions within Saturn's interior, where helium rain, layered convection, and differential rotation may produce a magnetic dynamo that behaves differently from those in other planets. Saturn's quiet magnetosphere, comparatively less turbulent than Jupiter's, allows for detailed studies of plasma interactions, dust charging, and the subtle movements of charged particles trapped in magnetic fields. The behavior of Saturn's auroras also reflects the planet's magnetic uniqueness. Unlike Earth's auroras, which are primarily driven by solar-wind interactions, Saturn's auroras often respond to internal processes: the rotation of the planet, the distribution of plasma from Enceladus, and the dynamics of the magnetosphere. These shimmering polar lights provide clues about Saturn's magnetic environment and the interactions between its atmosphere, rings, and moons. As the number of discoveries grows, the Saturnian system becomes not merely a collection of objects, but an interconnected ecosystem of physical processes. Dust from rings rains into Saturn's atmosphere. Geysers on Enceladus feed the E-ring. Titan's thick nitrogen atmosphere may contain traces of organic compounds that originated from photochemistry influenced by Saturn's magnetic environment. Ring particles reflect sunlight that modulates temperatures in the upper atmosphere, and moons exchange material through impacts and gravitational interplay. Every part influences the others, creating a cosmic web of cause and effect. From the standpoint of astrobiology, Saturn represents one of the richest hunting grounds in the solar system. Titan's thick atmosphere and surface liquids provide a natural experiment in prebiotic chemistry. Complex organic molecules snow out of Titan's atmosphere, accumulating on its surface and potentially interacting in ways that generate novel chemical structures. While Titan's surface is likely too cold for Earth-like life, its subsurface ocean, if present, could harbor more favorable conditions. Enceladus, by contrast, offers liquid water, organic molecules, and geothermal activity in a single package, making it one of the most promising locations for life as we understand it. Future missions may aim to sample Enceladus's plumes more thoroughly or deploy landers to Titan's lakes, seeking evidence of exotic biochemistry or microbial signatures. The prospect of life in such alien environments challenges our definitions and imaginations. Could Titan host methane-based microorganisms adapted to cryogenic temperatures? Could Enceladus sustain simple microbial ecosystems powered by chemical reactions between rock and water? These questions stretch scientific boundaries and hint at the vast diversity of possible life-bearing environments in the universe. Saturn's rings, for all their splendor, also reflect deeper truths about cosmic cycles of creation and destruction. The material in the rings may be remnants of a moon torn apart by tidal forces or the reprocessed detritus of collisions that shattered ancient bodies. Their shimmering brightness masks the violence of their origins. In this sense, the rings are simultaneously monuments to destruction and templates for creation. The processes that grind down icy particles also create the seeds from which new structures emerge, as moonlets assemble and disassemble in a ceaseless dance. Studying these processes teaches us about the early solar system, when planetary rings and disks were common and served as nurseries for the formation of moons and worlds. Saturn's rings thus preserve, in a state of arrested evolution, the kind of environment that once surrounded all young planets, including Earth. They offer a window into the past, a glimpse of the forces that shaped planetary systems long ago. As we extend this narrative toward a conclusion, the central truth that emerges is that Saturn and its magnificent rings represent a convergence of beauty and complexity unmatched in the solar system. The planet is a dynamic blend of atmospheric physics, internal heat, magnetic mysteries, and seasonal rhythms. Its moons form a gallery of worlds, each with its own story, from Titan's methane seas to Enceladus's hidden ocean and Iapetus's sharp contrasts. The rings weave these stories together, acting as both relics of ancient events and active participants in shaping moons and planetary behavior. To contemplate Saturn is to embrace both the known and the unknown, the measured and the mysterious. It is a reminder that even after centuries of observation and decades of spacecraft exploration, the cosmos retains its ability to surprise. Saturn stands as a pillar in our quest to understand the universe, a world where science meets wonder, where icy particles trace the music of gravity, and where each new discovery opens the door to further questions. Saturn's story is far from complete, and perhaps that is part of its enduring fascination. As our instruments grow sharper and our missions more ambitious, the planet continues to invite questions that challenge the boundaries of human knowledge. Future explorers may probe its deep atmosphere, sample ring particles in unprecedented detail, or even land on the surfaces of its moons to search for chemical or biological signatures. Each discovery will not merely add facts, but reshape our understanding of planetary formation, orbital dynamics, and the conditions that allow worlds to harbor life. In contemplating Saturn, we are reminded that the cosmos is not static, but a living, evolving tapestry, where even structures as seemingly permanent as its rings are transient on geological timescales. The interplay of gravity, motion, chemistry, and energy we observe around Saturn mirrors processes that have occurred across the galaxy, from nascent exoplanetary systems to distant ringed worlds yet unseen. The majesty of Saturn lies not only in its visual splendor, but in its ability to connect scales, phenomena, and disciplines. It bridges the intimate and the immense. Icy grains dancing in narrow rings, moons with hidden oceans, storms that dwarf continents, and magnetic fields that stretch thousands of kilometers into space. Observing Saturn challenges our notions of size, time, and possibility, inviting both scientific rigor and philosophical reflection. Its rings, moons, and atmosphere are not merely objects of study, but reminders of the universe's capacity to craft elegance from complexity, order from chaos, and permanence from ephemeral processes. In the final view, Saturn stands as a cosmic symbol of wonder and discovery. It is a reminder that in the vast reaches of space, there are worlds whose beauty and mystery inspire awe and drive curiosity, urging us to look deeper, think broader, and dream further. The planet and its rings exemplify the delicate balance between the familiar and the alien, offering both answers and new questions. Saturn beckons humanity to continue its exploration, promising that with each observation, each mission, and each leap of imagination, we come closer to understanding not just a single planet, but the principles that govern the cosmos itself. In Saturn, the universe has set a stage for discovery that is as enduring as it is magnificent, a testament to the endless possibilities waiting for those who dare to reach for the stars.